Okay, cool. All right, so welcome everyone to lecture number 3 for the database programming in practice. Today lectures, we're going to talk about data organization. So, well, just to let you know, you may, for some of you, you may expect that this course will be about using database management system or SQL only. Well, I'm trying to make this course much more fundamental, so you also know the technology as well. Okay. In this course, it's more like you're gonna learn bits and pieces in order for you to decide whether which database technologies you should use. Okay, that is why what I'm saying in the first lecture is that there will be a system perspective as well, and this will be one of the system perspective part. Okay, last week we mostly talked about something may not be that related to databases, right? It's more like a Python file IO, right? Which is used to do something that we call data persistence. But in this week, it will be closer to the database. If you remember the definition of the database is the organized collections of data, right? Structured data. Basically, means that you need to organize the data as a database. And this class, we will talk about that part. Okay. Just to let you know, solo project 1 due on December 16th, basically 2 weeks from now, less than 2 weeks from now. So if you haven't started, you must start. Okay. Well, I'm trying to say this because it's not like the PP last semester that is not that long. This one's quite long and more difficult. So you may want to take time so that you can spend some time on working on it. You can spend some time asking our teaching assistants. Both are important. Okay. If you have any questions regarding solo project number 1, feel free to drop in forum. Okay. As I tell you, we are not allow you to ask the TA directly regarding your solo project number 1 unless it is very personal. If you would like to ask one of us, you post it on forum and one of us will answer you, or maybe more than one of us. Okay. So on December 16th, and right after that, there will be a period for you to do checkout. So still, we still need to do checkout. So, well, I just want to add that the project deadline will be before, so December 16th, and then for the whole week, December 15, 16, 17, 18, 19, that will be the period for the checkout. If you want to, you can also do checkout like after the due date of the solo project without getting any penalties. Okay, but if you submit the solo project late, then you will need to lose you need to lose some grace days, right? If you just deplete all the grace day, then you will get deduct with points. Okay, any questions regarding solo project number 1? Oh, by the way, I think this is a very good time. If you have any questions on solo project number 1, feel free to ask me right now. Again, I just want to add that if you haven't started, it's maybe too late. It's not easy, this project is not easy. Any questions regarding project number 1? Okay, let me ask you. If you have taken a look on solo project number 1, can you maybe show some thumbs up, put some emoji? I see 2. Oh my gosh, only 2? Okay. Any other of you? 3? Okay, see 3. So what about the rest? 20s of you. So again, I'm trying to be truthful that if you haven't started now, you might be a little bit too late. So please get started as soon as possible. Well, it is not that difficult, but it's difficult. Okay, so you need to spend some time. Okay, right? So before we get into the data organization part, the lecture, the actual content, I would like to start with the motivation to give you an idea of why you should learn about data organizations. Okay, so assume that there is a new owner trying to open up a store, right? Sunny Day Goods. So Just a disclaimer that I generate this picture from Gemini, so yeah. All right, and well, there is a new owners, right? And there is like some of the customers trying to get into this store, right? So this is a very manual store, no computers. Let's say if, so you can see that there are a lot of items in the store, right? So assume that you are a customer. You would like to buy maybe a door, right? You need to you need to go to the owners and then ask him, hey, what is the price of this door, right? So imagine that, right? Oh, there's many customers, this girl, this boy, even this cat, trying to ask the owners, right, about the price of the product of interest, right? And the problem is that if these owner, they just like, oh, they just put like the price of the products, scatter it on like all of these books, it would be so hard to find it, right? It may not be that hard, but it would take time, right? If the price of the product are not organized well, right? That's the point. We talk about data organization because we would like to answer the questions or the queries fast. Not only fast, but it must be correct. So correct is a top priority. Then the speed is the second priority, the second top priority. So even though I say this is top priority, but the first one, the must one, is the correctness. You don't want to tell wrong price to the customer, right? So this is the point. The goal for this lecture is about to answer the queries. The query basically means a question, okay? To answer the queries or the question fast, correct, and fast. So let me ask you this. Let's say you are an owner. How would you keep the data? Well, any ideas? If you have any ideas, drop in the chat. Feel free to drop in the chat. Or maybe you can open up a microphone as well, right? As an owner, let's say you are an owner. Let's assume that you are an owner. How would you keep the data, the price data, so that it is easy to find? Any ideas? No, never mind. So, as an owner, rather than you scatters all the price across all of these books, you would like to organize the data, right? Sorry, organize the data. Maybe in some way like this. Okay, you have a book, like in some sense, in some structures, right? Plan with a price of the product, book with its price $20, a fish with $5, something like this, right? So it would be easy, right? So you can just open this book up and then check the price of each item. And then, oh, you can see the price and you can tell the customer. So the customer can easily buy your stuff, right? So the solutions to answer queries fast is to organize the data. In the lab, yesterday when Indy taught you about 5IO, right? There is the first assignment, the first lab assignment that he trying to, he have a CSV file, right? And then he asks you to write a functions to query, to answer the queries, right? Something like that. If you organize the data well, it will be very easy to search for the data. It'll be very fast. Okay. But this course focus, we're not gonna organize the book. We will organize the data in computers, right? We use technologies. So today's agenda, there will be a lot of them. We're gonna talk about structured data versus unstructured data. We're gonna talk about some insight in the computers. So last week we talked about that. If you want to keep data alive, you need to keep data on disk, right? On the persistent devices. So, but data from this, it cannot be used. Data can be seen by the computers if it is in the CPU. CPU is like a brain, you know. This is like a bag. So you need some way to make sure that your brain gets data from the book, right? So you need to bring information from the book to the brain first. And we will talk about that in the second bullet point. The third bullet point, we'll talk about some models for structuring data, for organizing data. And the last one, we'll talk about the file formats that people typically use nowadays. Okay? So first, let's talk about structured versus unstructured. Just to recap, database. The definition of the database is basically an organized collection of data. When we talk about a collection of data, we are not talking about a single piece of data, right? We're talking about multiple pieces of data. See? So, for example, in the database, you could have the informations of a book, a plant, or a door. 3 of them, like this. Okay? Then, for each book, each plant, each fish toy here, you may have the descriptions describing it, which is the data, right? The information for each piece of data, right? So you can see that in this case, each items here, we describe it as a text. But these texts, we describe each item as a text, right? For example, the first one, a book. This is a book. The title is Indie in Ollie's Land. The author is Pumzi. The price is $20, right? So, but for the plant here, this is a plant. $15 is a price. The type is Pothos. The age is 2 years old. You can see that the way we organize pieces of informations, they are not exactly the same. Okay, they are similar, but you can see that the price is right after the name of the items, right? For the plant. But for the book, the price is at the end of the statement. Sorry, at the end of this paragraph of the piece of information. So, if we don't organize the data like this, and also you see that for plant, the plant has type, right? The book has the authors, right? The fish has the factories, the models, right? Well, you can see that for each item, they have different properties, right? For the book, okay, the same property would be the name of the item, right? The book, the plant, a fish toy, right? The price here, okay, that's the same properties. But for the factory, the models, the type, the authors, they are different properties. So if the data is not organized in the same way, are not structured in the same way, holding different properties, we call them unstructured data. So the title here says that hold different properties. This is one of the property for the unstructured data. But mostly they are structured in different ways. Each piece of data, the information for each piece of data are organized, are structured in different ways. That is what we call unstructured data. The problem is that if you want to extract data, for example, if I give you this data and I say that, hey, give me the price of the plant, okay? One way of trying to do is this, okay, you read until you find maybe a dollar sign like this, right? once you find a dollar sign, then, okay, I can assume that the next one is a price. But is this always the case? So let's say that if we want to find a price of a fish toy, okay, oh, I see this dollar sign, so 5 is a price, but I also see this dollar sign, and I see some text. Is this a price? You see, this is a problem of letting people interpret data by themselves, right? So if you want to extract data, you need to interpret by yourself. And this is not accurate and good, right? So imagine. So basically, if you would like to write a program for this, it will be chaotic. It will be hard. You may want to use AI to help you, but AI cannot guarantee 100% correctness, right? So you see the problems, right, of the data when the data is unstructured. Most of the time, if the data is unstructured, you can just only you could just get the exact answers. Most of the time, you may get like some estimation, right, with some margin of errors. Okay. On the other hand, if you structure the data neatly, like this, you see now a book here, you have like the label for each property, like product, a book, right? Price $20. Description: the title is Cindy and Dolly Lane, the author is Poomsy, right? Product: plant, price $15. Description: the type is pothos, something like this, right? Okay, if I ask you, can you get the price of a book? You just need to get into this label, right? Price, and then you can graph the value right after that. And you can do it for all the data because they are structured the same way, right? For all the items, the informations are structured in the same way, right? So these the labels here, product, price, description, are what we call fields. Fields, 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 right? If you want to extract data, you write the programs, right? Okay, this is pretty similar to what you have yesterday. So I hope that you understand this program. First, we have this product.txt, right? So we have product, price, description, product, price, description, product, price, descriptions, right? Well, I need to say that these are in the same line, okay? These are in the same line. These are in the same line, right? It's not in a different line. It's just like the space that I use in this slide is not that large, so that's why it get truncated. Oh, sorry, that's why it get rapid. So if I want to write a program, one of the way is, okay, one of the way is, okay, I open the file with the read mode, read only mode. You have learned this. Then for each line, so this for loop is basically you iterate through each line of the files, right? Okay, you product first, and you split here, with the column, so you get like the product, right? And you split the column, so basically you're gonna have an array, a list of 2 elements. The first one is product, the second one is book, right? So for the product, you get the book, right? And then you get the next line from the files. You split it using the same one, right? Colon space. So you get the price, and if you get the second element of it, then you will get 20, right? Then you do the same descriptions, and then you go to the next line, you split it with it, you grab the second element. So basically you get all these description, right? And I can loop through it until the product name match with the product of interest. If it match, then you can print the price, in which it is the price of the product of interest, right? And then you can break and then get out of the loop. If not, then you can get into the next line and then go ahead, move on. See? Right? You understand? Well, if you don't understand now, let me warn you that you at least need to understand this code, right? So you can see it is pretty easy to craft a Python code or program or code or programs to read and extract data, a piece of data, field or values accurately, right? It's very accurate here. So in this course, we are not talking about how should we organize data for unstructured data. That way, that one, we will not talking about in this course. That is hard. Sometimes you may encounter it and you may need to deal with it, but for this course, we will only talk about structured data. That is more easy, that is easier, and for me, it is a good foundation. It is a good fundamental for you, right? So now you know what is structured data, what is unstructured data, right? What are the pros and cons, right? So any questions before we move on? Any questions? Do you understand so far? I hope you understand, right? So this is about data organizations, right? In this course, we only talk about structured data. So the question is, how should we organize data, a database, so that we can answer the query fast? Okay, the goal is how should we organize the database for structured data so that we can quickly extract the data or answer the query fast and correct. So before you know that, you need to understand how computers work first. Well, I'm not gonna teach you the entire things about how computer works. I will teach you only a part that is important for these lectures, okay? If you want to know more, you may need to take some intermediate level course to so that you understand how it works, okay? But if you want to get it fast, you need to know the process, right? So that you can optimize the process. It's just like when you are in the factories, right? In the factories, if you see the whole process, right? The whole pipeline, you may have an idea that, hey, if I remove this, it will make the process faster, something like that. This is the same. I'm gonna depict you with the whole pictures of how computer works when we interact with data, okay? So that you have a glimpse of, okay, if I would like to make this faster, I should cut this off. I should do this. I should do this. You have an idea, okay? I can tell you right away that this will be in the exam. Not this part, but the entire lecture, okay? Well, I mean, basically every lecture will be in the exam. Right, so let's recap last week, right? The storage hierarchy, right? We have the last layer, the slowest layer, but the cheapest one, which is the secondary storage. Here, I merge hard disk drive and SSD together. We call these I/O devices. I/O stands for input output. So in typical computers, when we call I/O devices, we are referring to hardware that provide input to the computers, and the hardware that will receive some output from the computer and then display or like show it back to the users. For example, speaker is also an I/O device. It is an output device, right? A mouse is an input device. A keyboard is an input device. Hard disk drive and solid state drive is also both input-output device, because you kind of like provide data or information back to the hard disk drive, right? You write it on to the hard disk drive. You also read the data from the hard disk drive as well. And if you remember correctly, I told you that the files that are persistent data are stored on disk. Okay? Files are stored on disk. Okay? So I will put it here. So let's say that I have product.txt. Okay? Is this on disk? Right? So whenever we want to read these files, we need to put it into memories. So this files on the disk, we need to read it onto memories. The way computer typically read it is that basically all the files on the disk, most of the files on the disk are chunked into pages. So let's say we have a file, a huge file, like this, right? We chunk the files into something that we call page, right? We have multiple page per files. Some file could have only one page. It depends on the size of the file, right? And then when we read the files onto memories, we only read a page. We're not gonna read the entire files because that sometimes if you have like 200 gigabyte of files, it would take a lot of time, right? So we will read just only a piece that you would like to read. For example, this one, I would like to read this file. Then I will pick like the first few page, the first page, only the first page, right? And bring it to memories. So this is the amount that I need to read the data from this to the memories, okay? The typical page size is 4 kilobytes. So per times, typically, we read 4 kilobytes. If I want to use, let's say, if I want to access like more, right? If I want to say the fish toy, I also need to bring this page onto memory as well. So per time, I bring 4 kilobytes, like this, okay? So we're not gonna like, okay, if I want to get only the first line, I will bring only the first line. Typically, computers do not do that, okay? Typically, but in the hacky way, you could do it. But typically, when you use computer in the typical way, mostly, if you want to read the first line, you need to read the whole 4 kilobyte, okay? Just a remark that this is definitely not 4 kilobyte. 4 kilobyte must be a lot more than this, okay? This is just an example. Any questions? Because this will be complicated. Any questions? So basically, when we read a file, we're not going to read the entire file onto memories. We only read a page that is relevant on what you want to read from the files, and we bring it onto memories. All the files are chunked into a set of 4 kilobyte chunks, okay? I cannot say all the files, most of the files, typical files, right? Then, now you bring a page onto main memories, or basically which is the DRAM, right? But there is a cost because every time you move something from the I/O devices onto memories, you create data movement. You move data, right? We call it data movement. Data movement takes time. You move data from one place to another place. It takes time. Okay. Again, so now the data is on memories, right? On the main memories. Can we use it now? No, not yet. The data can be used only if it is in the CPU. Okay? At least it needs to get into the cache. And in the cache, it must get into the registers, which is the CPU memory storage. Okay? So, okay, from the main memories for each page, again, the similar things. If you want to move to the next tier, right, from memory to cache, you do the same things. But this time, we are not go page by page. We go cache line by cache line. Cache line is basically a page, but the size is a lot smaller. Cache line, one cache line, one cache line is typically 64 bytes. 64 bytes. That is a typical size for the one cache line. 64 bytes, basically 64 characters. 64 characters. So if you want to bring from data from on memories to the cache, you need to bring 64 bytes per time. Okay? Per time. And yeah, since you bring it in, then you also create data movement as well, right? From I/O device to memory, you create data movement. From memories to cache, you can also create data movement. Well, since hard disk drive or solid state drive are slower than DRAM, so this data movement will be more expensive. This one is cheaper because we're reading from main memory or DRAM, which is a lot faster, right? So every time you're trying to read data from a file, it takes time because it does data movements. Okay? Any question? You still there with me, right? Oh, we see the quiz. Because today we also have a quiz. If you don't understand, then you won't be able to do the quiz. Okay. Righty. So, to summarize, every single step, if you want to read data from this, you must read the data from list and bring a page into the memories. Then from the memory, you need to bring a cache line onto the cache. And then actually there is another step here, which is onto register, which is in CPU. And this is the final stage, okay? This is also, you need to do data movement. But this will be the cheapest one. Okay? So, these together, the goal, if you want to make it fast, if you want to access the data on this fast, you need to minimize data movements between tiers. Okay, that should be your goal. If you want to make the query fast, if you want to organize the data so that query is fast, you need to minimize the data movement. Organize the data that in the way that you minimize the data movement. And this come into something that we call a principle of locality. Principle of locality is a principle telling you two properties of the data access, right? When we access data, right, we call it a data access. Principle of localities, we talk about the properties of the data access patterns, right? How the properties, the characteristics of the way you access the data, okay? So there are two properties. The first one is spatial localities. We talk about it a lot. The second one is temporal localities. We're not gonna touch about it today. I will speak on it a little bit right after we done with the spatial localities, okay? Well, for the spatial localities, the key is that if the data access patterns, or if the way you access data, only access the nearby data, like only access like the group of data that are close together, you have a lot of locality, you have a lot of spatial localities, okay? Well, the actual definition is that spatial locality is the likelihood of when will you access the nearby data, okay? It's more like a likelihood. So if the example of the data access pattern that have high spatial locality is, for example, example number one, you access the data from the same cache line. If you only access the data from the same cache line, and if that data is already in the cache, you can guarantee that the data will be only read from the cache. There won't be any data movement between other tiers except for the cache to registers, which means very cheap, right? It will be very fast. The next example. If you access the data, but from different cache lines, but still on the same page, right? But still on the same page. This time, let's assume that if that page is already on the memories, then you only need to read up to memories. You don't need to get into the disk, which is very slow, okay? For example, at first, I'm reading this part, right? Then this part is in the same cache line. If I only read this part, then I need to read from the cache only. So it will be very cheap. But once I get into this part, the yellow part here, now I need to bring new cache line from the memories to the cache. Creating data movements between memory and cache, which is more expensive than from cache to registers. Okay, which means if you do this, it will be likely this one will be more expensive, which means more time. Okay, if you use more time, right? Any questions? I think this is quite complicated, but at least you should know this, okay? So maybe let's see an example. Let's see more example. So let's say if the product, this one, we have a product file here on the disk, right? A file on the disk are chunked into pages, right? And typical page size is 4 kilobyte. So basically this file will be chunked into small pages. This is page. Let's say page 0, page 1, page 2, so on, right? If I would like to read 4 kilobytes of data, and if it is very fortunate that, hey, those 4 kilobytes of data are on only the first page, the page number 0, I only need to load 4 kilobytes onto main memories. This is the only cost that I need to spend, right? Reading for, this is the only movement that I need to do, right? We only need to move 4 kilobytes from this to memories, right? This is what I mean by spatial locality or access nearby data. If the data are grouped together, it is likely that you minimize the data movement. But let's see, if the data is not organized neatly, if the data are scattered all over the place, so let's say that this 4 kilobytes, you read the same amount of data, right? You read the same amount of data, 4 kilobytes. These 4 kilobytes are scattered across all over these files, not only on the same page, but onto different pages for the same files. For example, you read the first 1 kilobyte from the first page, okay? This one, you read from this one. Then you also read from this one as well. Now you access 2 pages, okay? So, okay, let me go back a little bit. So when you access this page, right, means that you move 4 kilobytes from this to memories, right? Even though you only read 1 kilobyte, but that is how computers typically work, okay? And then you move to the next 4 kilobyte, another page. This one, you only read 1 kilobyte, yeah, that's true, but you need to, what? Move 4 kilobyte from this to memories. Okay. Then let's say, oh, the third 1 kilobyte is on the second page, the page number 1. Well, again, what I need to do is move another 4 kilobyte to memories. And lastly, oh, it's on the last page, right? I need to move 4 kilobyte onto the memories. So in total, I move 16 kilobyte onto memories, main memories. Even though I only want to access 4 kilobyte, but based on how data are scattered randomly, it makes me need to read 16 kilobytes 4 times. Well, the technical term for this is what we call read amplification. So you amplify the read 4 times, right? 4 times. And this is the problem that we call random access. We access data randomly. We are not accessing data that it's close to each other, right? This data access pattern doesn't have good spatial localities. Another thing is that I want to warn you is that, okay, this is only about moving data from this to main memories, right? There is another issue for this random access. Let's say if I would like to read this page, right, 4 kilobyte. If I would like to read this page, well, which means even though I read 1 kilobyte, I need to read the entire 4 kilobyte. Okay, I need to read from the top to the end, from the start to the end. And if we put it on the hard disk drive, that is a magnetic disk. Inside of the magnetic disk, it will be like in the pictures. Okay, so you have a magnetic disk, and then if you have a head write, a read write head like this. Okay, and when you want to read the data, you need to move the read write head to the good position, to the position that you have data, right? Oh, sorry. Okay, like this, and you need to move the read write head to the good position like this. When it is at the position that data is, then it will read it by the we call the this a platters. It will rotate the platters until all the data are read, right? So it will be something like this. So for example, this one, I would like to read this page onto memories. It will be like this. You see? Actually, the one that is moved is a this, not the head. Okay, not this one. The visualization may get you confused. The one that is moved with a this. Okay, this one, the same. So this is a cost that you need to spend. There is an actual physical movement in the hard disk drive. Next, this is the problem. Another problem I want to solve. Let's say so this is the first page, right? This is the second page. The second page is before the first, the second page I would like to read is actually the page before the current page. For the hard disk drive, you cannot move most of the hard disk drive, you cannot move the platters. You cannot rotate the platters 2 ways. You mostly can rotate the platters only 1 way, which means if you want to access this point, you need to move, not the head, I'm sorry. You need to rotate the platters until you get back to where the data is. You need to move you need to do 1 full rotations until you get back to the data of interest. That is more expensive, right? For random access. Then you read it. You see, you need to do a full turn in which you only want to read 2 kilobyte, but in the disk, on the disk, you need to do like full turn, which cover megabytes or gigabytes of data. Again, what is moving is not the read write height. It is a platter or the disk. Okay, that is the one that is moved. Okay, and it mostly can move only one way for the platters. What I want to say here is that random access, or if the data are scattered all over the place and you need to go and grab data from this one to this one back and forth, it will be definitely slow. Definitely it will be very slow. And you should avoid. Okay? So what I want to say is, first, you make your data access pattern, or the way you access data, contains locality as much as possible, either spatial localities or temporal localities. Spatial locality we have already discussed, which is the data access pattern that tend to access nearby data. Okay, that is the access pattern that contains a lot of spatial localities. For temporal locality, it means that the data access pattern that tend to access the same set of data. You always access the same set of data. Okay, that is what we call temporal locality, which is another properties for the data access pattern. If you would like to, so basically, if you want to make sure that when you access data, it is fast, you need to avoid random access. That creates many data movements. You need to avoid data movement by avoiding random access, right? And you need to, and if you can avoid random access, you can also avoid physical read and write hash movement. Oh, okay, this is wrong. It is the spindle. Spindle is like under this, right? We will have like the middle here, in the middle here, which is, there will be a mechanics. There will be a component called spindle. Allow the disk to be rotate. So this is not read write head movement, the spindle movement. Okay. Actually, it's a little bit of the read write head, because we need the read write head to locate. So we have a read write head like this, right? Read write head will locate the data. When we write the data on the disk, we will like it like this. And it will have multiple levels. We are having multiple levels. Read write head here will move up and down here to get into the correct level, the level that data access, right? Spindle here will move the disk, will spin the disk, like will rotate the disk until you get into the good, until you get into the point that data access. Okay. Any questions, comment, concerns? Any questions, comment, concerns before we move on? Okay. So one of the way to reduce the number of data movement is to reduce the number of data that you need to access by removing unnecessary data. You look at this product text, right? You can see that the labels, product price description, we repeat this a lot, right? Why do we need to repeat this a lot? Why don't we just put this into a CSV format? So we only have the headers, right? Product price and description. That's it. We know the label already, and we just delimit the values by comma, right? You have already learned CSV from the last lab, right? By Indy. Why don't we just do this, right? We can reduce the number of data access, right? So if we do this, then it's likely that, okay, instead of this one, separate that into 2 pages, right? 1 page, 2 page. We could be able to fit this into 1 page, reducing the data movement between memories and a disk to memories, between disk and memories. See? Moreover, you can go more aggressive by doing binary encodings. So basically, one characters takes 1 byte. This includes 1 digit of integer as well. It typically takes 1 byte. 1 byte. So basically, if you have a value, a number of 9 digits, it takes 9 bytes. If you have a value of 1 digit, it takes 1 byte. But it is possible that for you to loosely compress any integers with 1 to 9 digits, including the negative integers, using only 4 bytes. So all of them would use 4 bytes evenly. You may think that, if I only have like 1 to 3 digits values in my files, why do we need to use this? Right? That actually is another benefit for storing the same value with the same size. So let's say if I store like if I have this set of data, if you would like to store it as a file, right, using a typical way, store it as a text, I need to store it like this, and between numbers, if I just pack it together like this, tell me how will you distinguish these 3 numbers? How will you split this text into 3 numbers? It's impossible, right? So if you want to do this, then at least you need to have commas or some delimiters, right? Comma is one of the ways you could use new line, right? Another way. So you take 1 more byte for the delimiters. Another thing is that, okay, if you want to access this one, you need to read this and then find commas. Once you find comma, you know that this is a second element, right? And once I find comma, I know that this is a third element. So we need to read sequentially until we get into the elements of that we want. Let's say if we want to get the third element, we need to read from the first, the second, the third, right? This can be different if everyone use the same size. For example, the first one, you take this chunk, 4 byte. The second one, we take 4 byte. The third one, we take another 4 byte. Tell me, if I want to find the third element, one way that I can do it is, I just need to access this. I just need to access the byte number 2 times 4 byte, which is the byte number 8. Right, so this is the byte number 0, byte number 4, byte number 8. Right? I can jump right away to the data that I want without the need to read from the beginning to the end. That's the benefit of doing binary encodings. It's not the benefit of doing binary encodings. It's more like a benefit of you storing the data using the same size. Okay? Right? When you should consider binary encoding. I already told you that. Okay, so it's 10 a.m. now, right? 1 hour has passed. How was it? Do you understand the things? Well, you know that since I changed the way I talk, which means we are about to do the quiz. Yay! Are you excited? Do you understand what I taught you? So again, it will be the same. I will show you the QR code. I will also show you the link as well. Okay? So I give you 5 minutes. 5 minutes to do it. Okay? So, if you are ready, I will give you 5 minutes. I will set up my timer. Set up my timer here. 5 minutes. Okay. Oh, shoot. Oh my god. Oh my god. Oh, it's gone. It's gone. Oh my god. Well, anyway, I set up my timer to 5 minutes. Then, 3. Ready to scan a QR code or using the link. Okay. 3, 2, 1, go. The link. Okay, I posted the link, and I hit this timer. 5-minute timer now. Tell me if you cannot access the link. Okay. We only have 1, 2, 3, 4 questions today. Well, the last question is quite long, so you may need to spare some time, right? Good. Oh, you guys are faster than I thought. 5, you have already submitted it. Wow. Well, you have like 2 minutes left. Oh, this time you guys are fast. Oh my gosh. Oh my gosh. I should give you only 3 or 4 minutes next time. Well, next time the quiz will be next for the next lecture, since it will be video only, so the quiz will be the quiz will be online. Okay, I will post a quiz and you just need to do it within the day. Within the deadline, right? The one after that will be on site. The quiz will be on site instead, so it will be a lot easier. Okay, 25 of you have answered it. 26. Oh my gosh. Oh, maybe today quiz is too easy. There is one tricky question, right? It's not that tricky actually. Oh, I'm so glad. See, look like you understand what I taught you. Feeling so good. Okay, 10 seconds left. If you haven't submit, just hit it. Just hit the submit button, okay? X 7, 6, 5, 4, 3, 2, 1. Yay, my timers. It's ringing. It's ringing. Just hit the submit button. Right. Okay. So there are 32 of you submitted successfully. Let's see. Let's see what's going on here. All right. So the first questions. Well, I'm so glad that I would say that most of you got it. Maybe not most of you. I believe that maybe all of you got it. Let me check the result. Oh, almost all of you. Oh, Indy will be so proud. Okay, there was one student. Okay, let me open it a little bit. Okay, can you submit it? I give you 5 seconds. 5, 4, 3, 2, 1. Time's out. Okay. Yeah, no more. That's too late. Okay. Well, let's see the question. The first one, many of you can answer it. Indy will be so proud. Oh my gosh. So I ask you, let's say if I write this Python code, right? Which is, the key is that I use the write only mode. W here, right? The write only mode. Then which of the following lines of code can be executed without causing errors? The first one, we read it, but we open the file as the write only mode. So it is impossible. There will be it's not impossible. They will give you an errors, right? The second one, we just write onto the file. This one is fine, right? This one is just we writing something and we open it as a write only mode, so it should be fine, right? Next one, we're trying to read something again, and this is unacceptable, right? Because we are opening the file as a write only mode. The fourth one, this one, we're trying to print some things from the for loop, right? With this, basically, we read each lines in the files, right? And it's in the write only mode, so we should not be able to read it. The last one, the close, I mean, you definitely should be able to do it. Okay, so the answer is the second one and the fifth one. The next one, the question is quite long. Oh, I forgot to put this one on. I should put this one on as well. Anyway, the previous question. So let's say that Poom has all of these follows and he has a lot of queries, and he gonna get different questions like, okay, 5 photo with more than 3, less than 2, more than 5, less than 2, between 1 and 10, 10 and 15, something like that. So how should he speed up his process? The first one, this one, is a little bit tricky. Well, the goal is to what? Improve or speed up the process, right? Let me ask you, if you upgrade your hardware to be better, can it improve the speed of the process? Yes, it can. So this one must be one of the correct answers. I didn't say that you cannot upgrade your hardware, right? I haven't said that you cannot do it, but maybe you need to try to do something else first, because upgrading hardware is something that costly, right? It's gonna cost you some money. Switch to a more accurate detection algorithms. Well, this one, it doesn't tell whether it will be faster or not, so this should not be the answers. Run the program once for all photos and store the counts in the files or the futures. looks up for the future lookups. Well, this definitely be the good answer that I would like you to answer, right? So you don't need to store the files. Entire file contain a lot of unnecessary data. You only need to store the counts for each files, right? Higher resolution is gonna take more times. Typically, gonna take more times. Shout at his computers. I'm glad that no one picked this option. Okay, I'm glad that no one picked this option. Yeah, but there is something interesting. There is an experiment that someone shout at hard disk, and it seemed to be faster. That's funny experiment, but just don't do it. Okay. The third one, this one pretty easy. All of you got it correct. I'm so glad. When you read a chunk of contiguous 1 kilobyte from this, who would move how many bytes onto main memories? Well, all of you answer 4 kilobyte, which is correct. But what I want to say is, it is possible that 1 kilobyte is in the corner between 2 pages. So let's say if you read 1 kilobyte, you can also read 2 pages at the same time. So another answer is 8 kilobyte. So both 4 kilobyte and 8 kilobytes are fine, right? You can answer both either of them. So that this one is not checkbox. So, well, I just want to tell you that, hey, 8 kilobyte is also possible as well, but I'm not going to deduct your score. Okay, the last one, the question is quite long. So we have Indy here, right, at the back. So basically, he would like to develop a web applications, right, to visualize the world map, to see the data, right, from the database. Problem is that the block, if you imagine the block contains tons of text, right, including the impressions, right, the impressions describe, express as ton of text. But the problem is the visualizations that they want, it doesn't relate it to those impressions at all. It's only related to what? To cities and songs, right? Only that part is important. So we only need to keep that. You don't need to keep unnecessary data, as I told you, right? Also, you could compress the block as well. That is another solution, right? The first one, yeah, I just put your hint here, so I'm glad that I almost said that I'm glad that no one answered it, but there are 3 students answer it. I'm not sure why. Maybe you are quick because maybe you need to be rushed because that is the last question, but this is not correct, even though he might try it. The third one, save his block as a collection of images and use them as a data database. Typically, images process slower than text, right? So this should not be the way to mitigate the problems. The last one, this is bad, because if you move his block to another machines in other countries, then it's so instead of you just access in the same countries, now you need to access data from different countries, which takes more time, right? I mean, even though there are multiple users across the world, scattered all over the world, but this should not be the answer unless the question say that, hey, most of the users are in Japan and you may want to move your machine to Japan. That could improve as well, the load time as well. Okay, well, I'm glad that most of you got it right and the average is so high. So, I believe that you all could be able to do my exam for this lecture now. I'm so happy. Okay, let's continue. Right. Okay, next one, we're going to talk about storage model. And this is important. Okay. So we talk about the fundamentals, the data movements, which is a key that we would like to minimize. And we talk about the technique to compress data, right? To remove unnecessary data, right? But there are other things as well that you need to consider. For example, let's say if I have this CSV files and I say that, hey, find the price of book. Okay, if I want to read this again, the contiguous text here would be in the same page, right? So it is likely that we need to read more data. But actually, if you want to find the price of book, you basically need only two first columns, right? The first two columns. That's it. So descriptions are likely to create unnecessary data access. See? But can you remove the description? Should you remove it? Well, sometimes another query may want to know the description as well. Maybe customer want to know the description as well. It's just for this query that it seemed to be not that appropriate. So you cannot just cancel. You cannot just remove the description columns. You still need to keep it. But how? How should you keep it? I show you 3 models for keeping data. Right? The models. When we talk about the model, we talk about something very logical, right? The first one is the NRE storage model, NSM. The second one is a decomposition storage model, or DSM. The third one is a partition attribute of cost, or PAX. Right? These 3 models are the basic models that people use to organize the data. Okay? Let's see the first one. The first one, basically, we store all fields for each row. For each row, let's say for this one, we have 3 fields, right? We have 3 values. We store them contiguously. We pack them together, which is basically what CSV file did, right? What we did. So it's good that most of the queries that you would like to run against these files need to access entire rows. If most of them access entire rows, this is good. This is perfect, because you need to, because when you read one page up, most of the file in that page will be read, right? Rather than CSV, we also have JSON files. So this is JSON files, right? We store field, value, field values, field value. This is pretty similar to the first one that I showed you, right? So this is another one, JSON file, and this is very popular in web applications. If you do web development, you will need to I doubt that you won't be able to use this very frequent. Okay, you see this a lot. You do web development, web application development. Okay? TSV file is like it's pretty similar to the CSV file. CSV file is the comma separated values. TSV is tab separated values. It just changed from comma to tab. Okay, another model, DSM. Wow, DSM is that in state. So in NSM, we store values for each row contiguously. We pack them together. For DSM, in state, we store values for each column and pack them together. For example, name. One of the ways you can break down your huge file into 3 smaller files. For each file, you only put values for each column together. That's it. The first file here, I only put names, right? The second file, I only put prices. The third file, I only put descriptions. The point that I would like to show you is that you see that I not only put on names, I also put on numbers here. This is a numbers to show the row numbers, right? This is a number of row. Sorry, this is a row numbers for each item. Why do we need to put this? Let's say if you store your data as DSM and and you get the queries that, hey, I would like to know what is the description of the book. If you don't store row numbers, you search for books, how would you know which will be the description of the book? You need to have the common numbers here, 1 and 1, and use them to, okay, this is from the same rows, something like that, okay? This is appropriate for queries that you need to access whole column, right? Or a chunk of a columns, only a single column, okay? If you want to access more than 1 columns, this might not be that good, I would say. Another benefit for DSM is that, hey, if you do DSM, then it is possible that value in the same columns are typically the same types. For example, in the price column, we usually store numbers, right? In the description columns, we usually store strings, right? So they will be all strings. If they are pretty similar, then it is likely that you can compress them. Okay? So, one way to compress it is, first, you can remove indexes. I just remove the index. Then, I just told you in the previous slide that, hey, we need this index. We need these row numbers to see whether, to grab other information from the same row, right? But why? This is because, imagine when you loop through these prices. When you loop through this, you know that this is the first element, this is the second element, this is the third element. So you use a number of elements as an index instead. That is possible. Okay, so you can remove the indices, and you can see that there are a lot of zeros here, right? If you store tons of zero like this, it's so inefficient. One way is that you can do something. You can do data compressions, and one of the data compression method is called RLE, or the run length encodings. So instead of you store 7 times, which take 2 bytes each, right? You only need to store something like this. Instead of 7 times, taking 14 bytes, right? You only need 3 bytes here. That's 3 times smaller, right? A lot better, right? And this typically happens with the columns that maybe it is an optional. It is an optional columns, right? It is a field that it is optional. Some people may not put the data into it, something like that, right? Another good thing of the DSM, of the compression, is that you can do processing in compressions. So the query is to find the sum of the prices, right? Normally, if you do DSM, well, you can just read the files and then you add them together. You use 9 additions, right? Looks good. You don't need to read any unnecessary data, right? You only read the necessary data. But if you further compress the data into this, you only need to read this. And instead of you need to do 9 additions, now you do 3 additions, but just 1 extra multiplication. Most of the machines, multiplication are more expensive than additions. But if the number of multiplication is 1 to like this, right? If it's just like 1 versus 6 additions, oh, that's a lot cheaper for sure. Okay, that is another benefit for DSM. If you store it as an SM, it is very hard to do this. I can say so. It will be very hard. Okay. Another one. Oh, I cannot. All the price, they are not. We cannot see any pattern. So how do we do it? How do we deal with it? By the way, I'm sorry for this because it should not be plus. It should be comma like this. I'm sorry. Okay. So, I cannot see any pattern, so I cannot compress it. So basically, I cannot avoid, but need to add them all together. But in the modern computer machines, in the modern computer system, there is a special instructions to let you, and it's in the CPU, in the modern CPU, to let you add multiple additions or in one instruction, which is a lot faster than you do multiple instructions, than you do multiple additions. This is called a vectorized instructions, or you could say vectorized execution or vectorized processing. Okay, this is faster. That's what I want to say. Okay, so I mean, doing one vector reduce may be slower than doing 1 addition, but if you compare with 3 addition versus 1 vector reduce can be a lot faster. Okay, maybe not by a lot, maybe 2 times faster, something like that. Okay, so this is the DSM, denormalized decomposition storage model. The last one is PAX. This is basically the hybrid one. So look at this part first. I would like you to look at this part first. Okay. So this is the actual things, right? So basically, packs is you partition rows into chunks, and each chunk you store it as DSM. So this one, we have at first we have Q files, right? We have product.csv. I break down into two chunks by rows. So I break that by rows into two chunks. For each chunks, you can see that I store it as DSM. So this is the DSM for names, right? This is for prices. This is for description, right? Which means you gain the compression benefit from DSM. You gain the vectorized processing benefit from DSM. You gain the you don't need to read data unnecessarily from the DSM. But let's say if you still need to read the entire data, you still have all the data in the same, close, it's still close to you. Then if you store it as DSM, it is in another file, right? This one you still in the same files. And it is close as well, right? Another things about this is that, hey, there will be a lot of chunks. Do we need to take a look into other chunks? Because if I need to take a look into other chunks, that will be the same, right? Because, I mean, if I want to find a sum or the price or something, I need to read all the chunks. That would not be good, right? So let's say if there is one chunk number 3, that all the price are zeros, right? One of the way is that, hey, we know that this chunk all price are zeros. So can I mark it that, hey, price min is zeros, max is 0, so you don't need to visit us. You can skip this chunk, right? You only need to read the max and min, and that's it. And you skip this chunk. So we reduce the data movement, right? We do data skipping. And this is what we call data skipping. We will talk about this more in lecture 9. But data skipping helps us a lot because it will help us see whether this chunk should be read or not, or should be skipped, okay? This will be in the part that we call metadata. In some sense, we could call it an index. And this is typically called min-max index or zone map. So there are a lot of terms. So this part is the metadata on an index, and the way that we keep min and max, we call it a min-max index or a zone map. Okay. So this is a PAX. Okay. Well, let's see the actual PAX in the real world. So this is the Apache Parquet, one of the very famous PAX file format, right? So if you look at this one, you see that, hey, oh, we have row groups, which is basically a chunk. So this one is a chunk. And you see that for each chunk, we store each column, the value in the same column contiguously, right? We pack the value in the same column together. This means if we want to access only this column, we only need to access this part, right? And we break down it into pages as well. See, the page 0 will be metadata, right? But the page, it will be, not only metadata, but after metadata we store values, right? Other page will be values. So basically, you just need to read only this column part, right? If you want to find some, right? For other column, you can just ignore it, skip it, okay? We break down rows into row groups, right? Groups, and for each group, we store it as DSM. That is a PAX, okay? We have another fancy way to look at it, right? Oh, we can also say that metadata is a header as well, okay? So for this one, we chunk row into 3 groups, right? Each group contains 3 rows, and we restore value. We store value in the column A. These 3 values together, this 3 value in column B together, this 3 value in column C together, we pack them together, right? You can check this link out if you want to see more in detail about Parquet. Another one which is really popular right now at the moment, but it's popular for the developers, but it's not that popular for the data use for the one who want to store data, right? So I need to say that many people use Apache Parquet to store the data that they want to do analytics right now. But for some developers who want to access data really fast, someone use arrow columnar format, which basically, hey, this is basically packs, right? You have rows, all this row you pack session ID together, the first value together, you pack this together as DSM, right? So this is the arrow columnar format. Why do I need to talk about arrow? This is because I would like to link you to polars. You heard about polars a little bit, right? Not sure. In the last semester, I have said the word polars once. In the next lab, people will teach you about polars. Polar is basically a data frame. Oh, data frame. Hey, data frame. That's basically our solo project number 1, right? So you will use the data frames the data frame libraries called polars, which is basically a new ER data frames. I would say that if you are getting to data science class, they will still use pandas. Pandas is a very popular library. I don't say that it is bad, but I would like you to explore new things that in the future people will be using, right? People will be adopting. Polar is one of them. And the good thing about Polar is that it is pretty similar to pandas. So even though you don't know pandas, but you know Polar as well, you can easily shift from Polar to pandas. Okay, it is a new era, and the statistic, the benchmark say that it is a lot faster than pandas, which is a very popular data frames libraries, by up to 25 or 30 times. That's a lot. Imagine you run things in pandas for a month, right? You try to do some queries in pandas for a month. If you do in Polar, you can finish it within 1 day. 1 month and 1 day, you see? That is how 8 seconds to 207 seconds difference. See? Also, what I tell you before, columnars, it uses Apache arrows, right? It uses Apache arrow that use columnars. It also have vectorized query engine doing vectorization. I believe it also do compression as well, but it haven't said so, right? Another one is also do parallel computing, which is just to make use of multiple cores in your machine. You know that most of your computers have multiple CPUs, not multiple core of CPUs, right? Multiple cores of CPU. Typically, when you write a program, it will usually 1 core, but since we have multiple cores, so if the programmer is good enough, they can write one program to use multiple cores, and Polar is one of them. And again, you try this in lab number 3. Yay! Are you excited? I'm not sure. Something very recent, just 2025. I think 1 or 2 months ago, not sure, but somewhere around this. There are just a recent PAX format called Vortex. Why? Parquet should be good enough, but why? You can see that in Parquet, there are so much complications, right? Those complications, so the way that we store as a PAX are the same, but the way people design about metadata are different. Headers are different. So Vortex is just a new way, right? They have new kind of layout. They have new kind of zone maps. Zone map is what this is the min max that I tell you, right? Min max. Some zone map can also carry the sum. So basically, if you want to find the sum of all the prices, you don't need to you may be able to not access any of the data part. You just need to access the zone map and then sum the sum up. That's it. You see? So this is a future file format that many people do. And the file format is still in research. You know, many people just research this the new file format because of what? We want to minimize data movement. We also would like to have a good data access pattern for new devices, new hardware devices, new disk. So I need to say that most of the file formats are invented when people typically use hard disk drives or the magnetic disk. But nowadays, we know that every people use solid state drive, right? Most of you use solid state drive. We still use knowledge from hard disk drive. So that is why the current research right now, they're trying to find a way so that we can build a file format that is suited for the solid state drives. See? And this is still in research, right? I just don't want to say what most, but a lot of contributors are from Carnegie Mellon. This one is very interesting. This is a file format that you can put WebAssembly. If you have written a web application before, you may heard about WebAssembly. You can put WebAssembly inside of it as well. Okay. This one, you see that it talk about compressions, right? Search accelerations, something like that. You see, this one talking about encodings, right? Something like that. All the things that we say, but in today's lecture, since this is the introductory course, so I'm not going to get into the details that much. If you want to learn more, read more. Okay, read this paper if you dare. Right? And that is for today's lecture. So in summaries, I just for this lecture, I only summarize into one statement. Database should be organized appropriately to be processed efficiently. That's it. That is the key takeaway for this. And I show you different way to organize database, right? And next one is that many data technologies, they use either NSM or PAX. So we're not gonna see DSM a lot, okay? Because most of the DSM, they move to PAX, right? NSM are for the transactional workloads, which is a workload that we tend to retrieve a row with many fields, right? We want to have a lot of fields. But for the PAX, we use it a lot for analytical workloads. Like if we want to find the sum, find the min, find the max, find the count, something like that for a single column or maybe like just a few columns, okay? For the next lecture, it will be videos. We will talk about, we will wear ahead of a database users. So this time is about system, right? Database system, but next time will be about database users. And see what are typical tasks people usually do with the databases. So we understand the workloads of typical, of how, like, so that we understand the workloads of the database. Okay? Before next lecture, next week, we still have the lab on Polaris by Pipum on Tuesday. Wednesday, we won't have this online class. It will be videos, recordings, because it is a holiday. I believe it is a Constitution Day. Okay, so we don't have a class, synchronous class like this, but I will post a video on it, right? I guess let people see you in the lab next week, and we will see you each others on December 24. Oh, that's Christmas. Oh my God. Yeah, we'll see each other in the Christmas day. Right, bye guys. Any question on solo project number 1?